I'm going to talk about chemical abundances in planetary nebulae, calculated from collision and excited lines versus optical recombination lines. This work is presented by me and my PhD student, Francisco Ruiz Escobedo, and we are from the Instituto de Astronomía, Universidad Nacional Autónoma de México. What is a planetary nebulae? Planetary nebulae are ionized envelopes around an evolved star, and great efforts have been devoted to analyze planetary nebulae to determine their chemical behavior, their ages, their distribution in the parent galaxy, and so on. And why planetary nebulae are important? Because they are the most luminous phase of evolution of their host stars, with luminosities of about 10,000 solar luminosities. And much of this emission comes out in a few bright, narrow lines. Also, planetary nebulae are indicators of metallicity of the interstellar medium at the formation time of the planetary, of the star, few giga years ago. And planetary nebulae mark the end of the active life of about 90% of stars, those who had initially between 1 and 8 solar masses, and which are called low intermediate mass stars, LIMS. Planetary nebulae are useful for the analysis of LIMS, their chemistry, their initial final mass relation, their binarity, etc. And they allowed chemical and evolution studies of the parent galaxy. Here I'm showing a typical spectrum of a planetary nebulae, a very faint continuum, and a lot of bright emission lines. The most intense lines are recombination lines of hydrogen and helium, and collisional excited lines of heavy elements such as O3, O2, nitrogen 2, neon 2, etc. For instance, the line O3 in 5007, this one very bright here, can emit ash mass as 10 to the 3 solar luminosities. Thus, planetary nebulae are easily detected at very large distances. And the analysis of collisional excited lines provides the physical conditions like temperature and density, and the chemical abundances of a lot of elements in the ionized plasma. Also, there are optical recombination lines called ORLs of heavy elements that have been detected in many planetary nebulae. These lines are very faint, typically 1/100th of H beta, and appear blended with the stellar lines or other nebula lines. So high spectral resolution data are required to detect them. Some ionic abundances can be obtained from some ores. In these figures, we show some ores of nitrogen, for instance, here, and oxygen in the zone of 4650 angstroms. Here we have another spectrum. In this case is nice 286, and here is VY22. So there are these lines, two optical recombination lines that allowed to determine chemical abundances. And since some years ago, we have obtained high spectral resolution data with the 6.5 meter telescope and microspectrograph at Las Campanas Observatory, and with the 2 meter telescope Sherry-Osk spectrograph at Observatorio Astronómico Nacional, Mexico, for a number of planetary nebulae in order to measure abundances from cells and from ores. And we have published some results in Garcia Rojas et al. 2012, 2013, Pena et al. 2017, and others. Our work and many works by other groups have shown that cells and ores predict different chemistry for the ionized gas. That's terrible. Larger amount of heavy elements are derived from ores, This problem, this phenomenon, is called the abundance discrepancy factor, ADF. Here, we present some preliminary results of data obtained at Mexico in 2018, 2019, for some very dense and compact young nebulae, CN31, BY12, BY22, and others. So, I'm sorry to present this terrible table, but it's just an example of the lines we measure for BY2. Hundreds of lines are detected, and we derived fluxes, line width, expansion velocities, all the possible things. From the collision excited lines, we determined plasma diagnostic. We determine electron temperatures and density in the plasma from different line ratios. In this diagram here, which is showing the temperature and the density. It is seen that temperature can be determined from oxygen 3 with these line ratios, from nitrogen 2 with these line ratios, and the temperature in this object in particular goes around 10,000 to 11,000 Kelvin. Density, on the other hand, can be determined by another line ratios, argon 4, this line ratio, sulfur 2 with this line ratio, chlorine 3, and also from oxygen 2 with this line ratio. And for this object, all these diagnostic ratios are showing that the density goes from about 5,000 to 10,000 particles per cubic centimeter. So temperatures and densities in the plasma are determined in this way. Ionic abundances. From these physical conditions and from the intensities of lines, ionic abundances can be derived, where we have used IRAF or Pena facilities to determine these parameters. And in this table, we show the ionic abundances relative to hydrogen plus of CN31, B122, B112, and the abundances of helium plus 2, oxygen plus, oxygen 2 plus, nitrogen plus, neon 2 plus, neon 3 plus, argon 2 plus, argon 3 plus, argon 4 plus, and sulfur plus 2, chlorine plus 2, iron plus, iron, etc. Even potassium has been determined, the ionic abundance of potassium plus 3. And here are the values relative to the hydrogen plus abundance. Total abundances then, derived from the ionic abundances, we add all the ionic abundances that we need to correct for some unseen ions. And then total abundances are derived from these ionic abundances and some ionization correction factors to correct for these unseen ions. ICF we use are from Kingsford and Barlow, 1994, and Delgado Inglada et al., 2014. And in this table, we shows the abundances of helium, oxygen, nitrogen, neon, sulfur, argon, chlorine for the same three objects I shown in the previous table. Sorry. We can compare these abundances with solar abundances by Absalon et al. 2009, which are shown in this small here. And we can see, for instance, is that comparing the oxygen abundance in the sun, that is 8.69, with the abundances derived for these three objects, CN31 And BY12 show solar abundances in the terms of oxygen. However, this BY22 is underabundant in oxygen. There are other important things in this table, but what I'm going to do here is to compare these abundances derived from the collisionally excited lines with the abundances derived from the optical recombination lines. These optical abundances or ionic abundances for oxygen plus 2 and other ions can be determined from the observed optical recombination lines. And the derived values for these three objects are presented in this table. You can see that we cannot derive the abundances from optical recombination lines for CN31, but we did it for BY22, BY21. And this is the ionic abundances of oxygen plus 2, and the results are here in the last part of the table. And we can compare these abundances for oxygen plus 2 with those derived for or from the collisionally excited lines. This is made in this table. And the ADF, the abundance discrepancy factors, are calculated at the bottom of the table. We see that the discrepancy factor in the case of BY22 is more than 4, 4.34, and for BY12 is 5.69. What does it mean? It means that the optical recombination lines predict 4 times more oxygen plus 2 than in the case of this object, 4 times more oxygen plus 2 than the abundance predicted from collisionally excited lines. In the case of BY, the discrepancy is almost 6. This is very bad. Discussion. Ionic abundances derived from collisionally excited lines and optical recombination lines for the same ion, oxygen plus 2, differ in photoionized nebulae. The discrepancy is a factor of 2 in H2 regions, but could be much larger in planetary nebulae. Even a factor of 100 have been reported for a few objects. For the object presented here, which are compact, dense, young planetary nebulae, we found ADF of about 4 and 6. The reason for such discrepancies are not well understood. However, it is crucial to determine which is the real chemical composition of the gas in the planetary. It's very important to determine the real chemical composition. It has been suggested that temperature fluctuations in the plasma or the inclusion of hydrogen deficient clumps in the plasma could be responsible for this difference between the chemistry predicted from cells and that predicted from ores. Besides, recently it has been argued that cells and ores can be emitted by different plasmas with different abundances coexisting in the nebula. The largest ADF seem to be related to closed binary system. And in addition, the analysis of the kinematics of some nebula support the idea that different plasmas are emitting collisionally excited lines or optical recombination lines. In this graph, I'm showing the kinematical behavior of ions in some planetary nebulae, such as is presented by collisionally excited lines, the blue points here. Here we have presented the expansion velocity for the different ions as a function of the ionization potential of these ions, which is representing the distance to the central star. the most ionized species are nearer the central star, while the low ionization species are far away from the central star. So this is the distance in this axis. In blue, the cells. We are going to see this special object, HB4. We can see this gradient in velocity, which is a normal gradient in velocity for an expanding plasma. The higher ionization species near the star show low expansion velocity, while the species far from the central star are expanding faster. So this gradient is expected. And the gradient is shown by the collisionally excited lines. In red, we have the same, the velocity, expanded velocity, as derived from optical recombination lines for the different ions. And we see a different behavior. These optical recombination lines, or the gradient from optical recombination lines, is much flatter. It's much flatter. So this can be interpreted as the collisionally excited lines are produced in a plasma different than the plasma that could be producing the optical recombination lines. And these plasmas are showing a different behavior, a different kinematical behavior. And the same is found in this other planetary nebula, NGC 3918. We have the gradient in velocities from the collisionally excited lines and a much flatter gradient from the optical recombination lines. So in these two cases, we can propose that collisionally excited lines are emitted in one plasma and optical recombination lines are emitted in a different plasma. There are at least two plasmas emitting this different kind of lines. There are other objects, for instance, this one, DY22, where the difference is not so noticeable. And the same in this one. What I'm showing here with the arrows is the behavior of, or the kinematics of oxygen +2, as predicted in blue by collisionally excited lines and in red by optical recombination lines. In the case of HB4, there is a huge difference of the velocity as derived from the collisionally excited lines and the optical recombination lines, and it is the same ion, okay? So they should behave equal, but it's not the case. And also it's not the case in this NGC 3118. The optical recombination lines is showing a larger velocity than the collisionally excited lines. In the case of the two objects, on the other hand, the velocities coincide for the same ion. This is okay. This is what should expect. So, what could be my conclusions? We present ADF, abundant discrepancy factors, calculated for some compact, dense, and young planetary nebulae. Our various values, this discrepancy varied from 4 to 6, which represent a major problem in the determination of the real chemical composition of the plasma. To know the nebular chemistry is imperative to understand the nucleosynthesis and evolution of the central star and their impact in the chemical evolution of galaxies. There are indications that collisionally excited lines and optical recombination lines can be mainly produced by different plasmas with different chemistry ejected at different epochs by the central star and coexisting in the nebula. It is very important to elucidate this issue. Then much better observations and much more work are necessary. We need to work harder. That's for ores are produced by different plasmas with different chemistry. It is imperative to determine the masses involved in these plasmas in order to determine if the real chemistry is that derived from collision helix lines or that derived from optical recombination lines. And I think that's all. Thank you very much for your attention, and a list of references are given here. Bye.